Ladies and gentlemen, could I have your attention, please? My name's Andrew Hamilton. I'm the Vice-Chancellor of Oxford University, and on this rather grey and dull October evening in Oxford, it's a pleasure for me to welcome all of you to this Oxford Martin School lecture series and a wonderful lecture that we will have brightening our day from Larry Brilliant, who no doubt will tell us things that will also challenge us and be most fascinating. It's a huge pleasure for me to be, as Vice-Chancellor, welcoming Larry and his wife. They were here on Saturday for the graduation of their son, and I had the honor of presiding at that graduation ceremony. It's my pleasure to welcome all of you, but I particularly want to call to the podium the director of the Oxford Martin School, Professor Ian Goldin, who will introduce Dr. Brilliant. And Ian, as many of you know, has been the director of the Martin School for the past 5 years. And prior to coming to Oxford in 2006, he was the vice president of the World Bank, and prior to that, the Director of Development Policy at the World Bank. And so it's a pleasure, Ian, to invite you to the podium to introduce Dr. Brilliant.
Thank you very much, Vice-Chancellor, and thank you for finding time in your incredibly busy schedule to be with us here today. It really is a delight to welcome all of you, and particularly Dr. Larry Brilliant and his wife, Girija, and our esteemed panelists who will join us and who I will introduce when we get to that section of the program. Dr. Larry Brilliant has a most fortunate name because it describes what he is, but not only what he is, who he is. He is a brilliant intellect, but more important, he has a brilliant mind and soul. He is the sort of person who cares, and has this combination of caring and competence, which is all too rare. And as we think of the challenges of the 21st century, and that is our job in the Oxford Martin School, we think about the looming stormy clouds, and we think about how they are to be lifted. And when one thinks about that and thinks about the key issue, not least of pandemics, which is amongst the worst of these possible storms, and you think about the work that he's done in his past and what he's doing now, one sees the light, and that is what is so exciting. The potential for great minds to come together in new ways and resolve the challenges of the 21st century. And I'm delighted that Larry's the first in our series of presentations and talks this term. I'll present the rest of them to you later in conclusion, just to remind you of them, but they're on our website. And it's his optimism about what modernity can bring, as well as his deep and profound knowledge that the complexity and connectivity, which is both the solution, is also the source of the potential crises going forward. And how you put together this incredible openness and globalization to be a source of strength and not a source of vulnerability is absolutely key in ensuring that we're able to navigate the coming decades. Larry is currently President and CEO of the Skoll Global Threats Fund, which deals with 5 key issues, in addition to pandemics, climate change, water security, nuclear proliferation, and the Middle East. It's a most exciting new venture, which Jeff Skoll has supported, which is seeking to not only harvest academic and insight, but to move the politics as well. And I hope he tells us something about that, not least in the area of pandemics. Prior to joining Skoll, Larry was Vice President of Google and Executive Director of Google.org, which is the philanthropic arm of Google. He has worked in many capacities as a foot soldier in the provinces of India, in the corridors of power, advising the President of the United States and chairing the Biosecurity Task Force. And in all of these, he shows the same humility, insight, and fortunately also sense of humor, which makes him such a wonderful friend. In addition to being a medical doctor and a professor of public health, he's been an advisor in many places. He was at the outset involved in the smallpox eradication in India, and he worked on that with David Heyman, who'll be joining us later. Worked on polio, on blindness, on disease surveillance, and on disaster. He founded something called the SIVA Foundation, which has given sight to over 3 million blind people around the world. And, of course, he's been involved in trying to make us all understand about these issues. Most recently, as the senior technical advisor in the movie Contagion, he was able to make it not only dramatically Hollywood, but dramatically real. He's also conceived a movie called The Final Inch, which was Oscar nominated, which is about polio eradication in India. His awards include the TED Prize, Time Magazine's 100 Most Influential People, International Public Health Hero, and 2 honorary doctorates. He's written books, articles, and, importantly, all based on this philosophical underpinning, which was his first degree. An ability to break down silos, to both understand the technical issues and what we need to do. Larry, it's a huge pleasure to have you here. We welcome you to the podium.
Thank you. Ian, thank you very much for that introduction. I'm exhausted. Vice Chancellor, thank you very much. It's wonderful to see you again. For those of you who take Oxford for granted, I have to tell you, as a newbie to an Oxford graduation ceremony, I found it thrilling. Hearing it in this room in Latin, it felt like an unbroken chain all the way back to Roman times. It was really something. I'm really honored to be here. Thank you, and thank you to the Oxford Martin School. So I was told to give a talk for a general audience introducing the idea of pandemics. I have 3 points that I'm going to make. 1, ceteris paribus. I've done my Latin. All other things being equal, if we do nothing else, there will be more pandemics. We bear the risk of entering into an age of pandemics. More and worse diseases emerging from animal zoonotic diseases. The causes of that I will go through, but they are fundamentally the causes of modernity. That's point number 1, if we do nothing else. Point number 2 is there's so much to do. New vaccines, antivirals, point-of-care diagnostics, new regional systems of governance, and most of all, better, faster ways to detect the first pandemic, the one that jumps from a monkey to a human, that comes out of a forest. Indeed, the hypothesis is, if we can find every new virus as it jumps species to humans, we have the chance to consider eliminating pandemics in our lifetime. Oh, it's a terribly ambitious thing to say. It sounds preposterous. But then so did the eradication of smallpox, the eradication of polio. So the third of my points is that I think the first 2 are competing lines in opposite directions. And the third is that you have a choice. We all have a choice. How much are we going to prioritize what modernity can do to solve a problem caused fundamentally by modernity? So I'm going to show some snippets from the movie Contagion. I'm going to talk to some of them, but because of that movie, I'm going to be able to let Kate Winslet do some of my talking, Matt Damon do some of my talking. And we'll see if that can't make it a little bit more entertaining, because otherwise this would not be a lecture that would brighten up the day. I should just tell you about the Skoll Global Threats Fund. Ian told you a bit about it. I'll end with a little talk about it. But in the Q&A, I hope you'll ask questions about nuclear proliferation and climate change and some of the other things, and ask what kind of crazy person would put all 5 of those into a single foundation when 100 foundations alone could be devoted to any one of them. I hope we'll have that question. One of our sister companies is Participant Media, which along with Warner Brothers made this movie. It was written by a wonderful screenwriter, Scott Z. Burns, and directed by Steven Soderbergh. My colleague Mark Smolinski and I acted as senior technical advisors to get the science right. In fact, we interviewed 200 of the top scientists in the country to try to get the science right. And I hope that you will find some of these snippets to illustrate some of the points that we're dealing with today.
Is anyone even working here?
Just get the cereal.
Jory, don't touch anything.
Help me. Here, take your gloves off. Here, give me your hands. You really rub this in.
I chose this scene because it has a Mad Max post-apocalyptic vision, which is what many of us fear would be, in fact, the case of a classic pandemic. Not a pandemic like H1N1, which we all suffered through a few years ago. H1N1 was a trial pandemic. It was like having the extra wheels on your bicycle to learn how to deal with a pandemic. Because we were really lucky. Because the roll of the dice that could have made it not only one of the most transmissible viruses in history, did not also make it one of the most lethal viruses in history. But we were lucky. It could have gone the other way. It should have gone the other way. Most of us thought that it would go the other way. We made the movie to show you what a real pandemic would look like instead of one that had so much hype and then left you with a vague sense of disappointment that the pandemic wasn't bad enough, which in fact was what most of the media said. But some of the smartest scientists in the world think that it's inevitable. I'm taking the liberty of quoting a Cambridge scientist. I hope that's not a problem here. But Lord Martin Rees, who has until recently had 3 of the best titles in the English language. He was the head of the Royal Society, he was the master of Trinity College, and he was the Queen's astronomer. Martin made a bet on one of the long betting online systems, and his bet was that by 2020, there would be a single event that would kill at least 1 million people. And if you talk to him, he'll say, I would have made that bet 100 million, but then I didn't think anybody would take the other side of the bet. So why is that? Why do so many scientists feel that we are on the verge of pandemics if we do nothing other than what we are doing? Well, because there are increases in human population. Because human settlements now push into animals' habitat. Because last year, Africans alone consumed just shy of 1 billion wild animals. And I know that when we talk about epidemiology and people think about sexually transmitted diseases, they think that's the most intimate way that humans can exchange viruses. But I assure you, the most intimate way that you can exchange viruses is to eat another animal. In China, in Laos, in Cambodia, where economic development has allowed people to buy more protein, to eat more animals, we have the closest and most intimate relationship that the most number of people have ever had in the history of humanity. With increased speed of travel, we're able to take a virus from an arboreal rainforest all over the world faster than we could imagine. In 1917, the Spanish influenza traveled around the world 4 times in a year. Imagine what that virus could do now. Well, how do we answer that challenge? We answer it first with the gating issue, which is find the new pandemic potential viruses. That's the gating issue. Of course, vaccines are the most important thing that we could have if we have them in our armament, antivirals. But if we don't find the virus, if we don't know where to apply our interventions, if we don't know where to send our rapid response teams and to have our point-of-care diagnostics and our genomic epidemiology, then all of that goes to waste. Surveillance rapid response containment. David Heyman's familiar with this cadence. This is what we did in smallpox eradication. And it's important that we find the right places to apply this speed of detection and response and containment. We know that there are hot spots that are more likely to be the source of H5N1, H1N1, SARS. We know that Southeast Asia is a more likely place from which respiratory diseases will come. South Asia is more likely to be a source for waterborne diseases, Africa for bloodborne disease. These are not hard and fast rules. We're talking generalities. But David is involved in an organization called CORDS, which we are involved in also, which is trying to reestablish regional governance between government-to-government health departments in areas that are most likely to be the places from which new viruses will occur. So it's very important that we establish not only rings of immunity around a virus, but we establish rings of governance around a new virus. And where will those viruses come from? Where will be their ultimate origin? It could be deforestation, knocking down trees, bats being released from their ancestral homes, moving into human habitations, living in a barn, sharing an apple with saliva, with a domestic animal, being cooked for supper. Sharing blood with the chef. And then with Gwyneth Paltrow, who's going to get on a plane and go to Chicago in a minute. So, if we think of this entire hermetically sealed system, when we talk about a pandemic, we're talking about an epidemic which occurs in more than expected frequency, in 5 continents, spreading some big number of diseases. Let's look at one disease that we know very well, because we know it almost from beginning to end. Let's look at smallpox, because we don't know where it really began, but we know that as long as 3,000 years ago, smallpox was very common. We know that one Egyptian pharaoh, Pharaoh Ramses V, had smallpox, died of smallpox. We know that even when Larry Page and Sergey Brin, my former colleagues at Google, when they were born, there were 2 million deaths a year from smallpox. We know that smallpox killed over 500 million people in the last century. That's not a wordo, that's 500 million people were killed in the 20th century by smallpox. And more importantly, as a moral lesson, we know that the 1% is not safe from a new disease for which there's no antiviral or no vaccine. This is one of my favorite slides in public health. It's not my favorite slide because I like the idea of sovereigns being killed. I want to be clear about that. It's my favorite slide because anyone who looks at this has to come to the conclusion that we're all in this together. That a new pandemic for which there's no cure, that we're just hearing about, we're all at risk. Not just the 47%. Let me tell you a little bit about what smallpox looks like, but let's use as our vantage point, not a doctor, let's look at it from the perspective of a mother watching her child develop smallpox. And I warn you in advance that many of these pictures are hard to look at. So here's a young boy born in Pakistan. His brother had smallpox. There was a CDC epidemiologist there. We'll call him Muhammad Ali for now. And the epidemiologist had a camera, and he photographed him every day of the disease. So you can see what that disease looked like to his mother. Day 1, day 2, day 6. Already you can begin to see the pathognomonic, the characteristic lesions of smallpox. Day 9, day 13. By day 13, you can see, as an epidemiologist, this boy will live. He'll be scarred for life. But he's one of the lucky ones because as many as 35% of children who got smallpox died. And by day 20, he's out of the woods. And just a little bit about smallpox. It's person-to-person spread. It's respiratory. Has an incubation period of 7 to 17 days. About 70% of you would be getting smallpox if I was here talking very loud and broadcasting my respiratory spread voice. It can be prevented by vaccinations, by cowpox, by previous exposure to smallpox. And unusually in vaccination after you've got the disease within 4 days can interdict it. And here's the question about vaccines. Vaccines are the most wonderful thing we could possibly have in public health. Bill Gates' life work has been to flip two ratios. 20 years ago, only 20% of kids under 5 were vaccinated against the major killers and cripplers. Today, 80% of kids worldwide are vaccinated. When he goes to heaven at the end of his life, he's got a really good get-out-of-jail-free card. But we had a vaccine against smallpox for over 200 years, and we didn't eradicate smallpox. We had a vaccine against polio for over 70 years, and we haven't yet eradicated polio, although I am ever optimistic. In fact, here's a really good slide to give you an idea of what happened with smallpox, beginning with 1967 when Professor Vladimir Zhdanov from the Soviet Union came to the World Health Assembly and challenged the entire world of nations for us to work together on the same team fighting against a common enemy. And you can see that spike. Now, that's when I joined the smallpox eradication program. Now, that's when David Heyman joined the smallpox eradication program. Now, you may wonder, what did David do to create that spike? I mean, he's a nice enough guy. What did you do to start that spike? Well, what he did, and 150,000 other people, is they went door to door to every house in India looking for every single case of smallpox, because to eradicate it, we had to find every case in the world at the same time. And when David went door to door with all of his colleagues, trying to find every case of smallpox, they found a higher percentage of cases than anyone had ever found before. So that is not really a spike of an epidemic of cases, that is a spike of an epidemic of reports. And that's the whole thesis of why early detection is so important. You have to find the right disease in the right place by the right method for the right reason, or else you wind up with aberrations in your data. And how did we eradicate smallpox? Well, this is the other lesson for how we can try to challenge ourselves to go after pandemics. Everybody has been doing mass vaccination, but if there's an outbreak of smallpox in Oxford, it does not help if we vaccinate in Tokyo. It just doesn't. You have to vaccinate where the cases are. But that is now so clear. But it wasn't so clear in 1968 when a young medical officer who was working with his church in Nigeria in the middle of the Nigerian Civil War found himself confronting an epidemic of smallpox. And Bill Foege did not have enough vaccine for everyone in the village. And he asked himself, as a Lutheran, as a Christian, as a moral person, what do you do when you don't have enough vaccine and you can't do what was then the received wisdom, vaccinate everybody? And he said, the moral thing to do is to give the vaccine to those who need it the most, by which he meant those who were closest to another case of smallpox or who had come in contact with him. And that led to this idea of active disease surveillance followed by what is now called ring vaccination or containment vaccination. Now, this is an idea that is as powerful as anything you can do in the lab, because it led to all of us going around carrying that card of a picture of Muhammad Ali and asking villagers, had they seen a case of smallpox like that? And I'm pleased to tell you that's my wife over there. She hasn't changed a bit. And this is what we did for social media at the time. There was no Facebook. There was no Google. But we put these everywhere, trying to tell people, if you see someone who looks like that, report them to us, because we want to find them. We put our signs on the backs of rickshaws in the middle of theaters. More importantly, David and his 150,000 best friends wrote on every single house in India. When was the last time a search worker was there, a vaccinator was there? That was our scorecard, written in something called Wet Geru on the side of every house in India. I want you to understand the scale, the obsessiveness, the analness that you had to do to find every case of smallpox in the world, because that's what we're going to have to do to rid the world of pandemics. And then the reward is this: the last case of variole major occurring in nature, Rahima Banu, whose disease took place in Bola Island in Bangladesh, and a certificate of disease eradication signed by all the health ministers, members of the World Health Assembly. Please remember, it took a village. It took all of us. It took people who were white and brown and black, all religions, all nations, working together against a common cause. And it particularly took the people whose names we don't remember. Not the big shots, not the ones with computers, not in Oxford talking to everybody, but the ones working on the field, risking their life for an abstract idea of how to eradicate the disease. And now we're close with polio. I won't spend much time on it, except my heart is in it, David's heart is in it. We are very close to eradicating polio. It is actually left in only 3 endemic countries. Unfortunately, one of those countries is Pakistan and another is Afghanistan. But India went 12 months without having a single case of polio. I want you just to understand some of the problems that we are up against so that when we talk about eliminating pandemics, we remember the ground game. Remember the foot soldiers.
परेशान रही अपने मेरे छोटे-छोटे 3 बच्चे थे है ना तो इनको स्कूल में भी पढ़ाती हूँ इनकी वजह से मैंने सोचा मैं क्या कुछ करना चाहिए पहली बार मुझे घर से कदम निकालना अजीब सा लग रहा था कि मैं कैसे करूँगी वरना मुसलमानों में कोई ये वाली ड्यूटी करने के लिए तैयार नहीं होता तो ये अब हमारी हिम्मत है क्योंकि उनके दिमाग में गलतफहमी हो जाती है कि ये पोलियो वाले हैं गलत पोलियो की दवाई नहीं है ये किसी और चीज़ की दवाई है हम कहते हैं नहीं हम मुसलमान हैं तुम भी मुसलमान हो हम कोई आपको गलत दवाई नहीं पिलवा रहा है मेरी फील्ड बुक में है पूरा सर्वे हुआ है 5 साल तक के बच्चे को मुझे बिना बगैर देखे बता दूंगी इस घर के अंदर छोटे बच्चे हैं मुझे मालूम मेरा एरिया है ना कि ये मुजरिन बाजी है और ये पोलियो वाली बाजी है
Tremendous pride.
सब मेरे को बुरखे में पहचान लेते हैं अस्सलाम वालेकुम मेहमान आ गए आप क्या फिर अब मैं डेली सोती भी हूँ तो ख्वाब में यही लगता है कि मैं हर बच्चे को रोजाना 1 हफ्ते तक दवाई पिला रही हूँ और 1 हफ्ता तो हमें सपने में भी यही दिखता है कि हम उस गली में दवाई पिला रहे हैं उस गली में दवाई पिला रहे हैं तो हमें बहुत
So let's talk a little bit about generic epidemics. This slide shows the last, from 1996 to 2008, how quickly the median pandemic potential disease in the world was detected. This is work of John Brownstein from Harvard. And in 1996, it took 167 days. If it takes 167 days to find an outbreak, by the time you get there, that outbreak could be all over the world. But by the year 2008, we were down to 23 days. Now, there's a lot of information here. I don't want to make it sound so simple. But some of the reason that we are finding diseases more quickly is because of digital disease surveillance systems. And it's very important that we find every case, whether digitally or by working in the field, because of the incubation period, which is how long it takes from one person to get the disease from another, and because of the reproduction rate, known as R0. Now, a lot of people have trouble with R0, so I decided to ask Kate Winslet just to explain it to you.
When will we know what this is? What causes it? What cures it? Things that keep people calm.
What we need to determine is this. For every person who gets sick, how many other people are they likely to infect? So, for seasonal flu, that's usually about 1. Smallpox, on the other hand, it's over 3. Now, before we had a vaccine, polio spread at a rate between 4 and 6. Now, we call that number the R0. R stands for the reproductive rate of the virus.
Any ideas what that might be for this?
How fast it multiplies depends on a variety of factors. The incubation period, how long a person is contagious. Sometimes people can be contagious without even having symptoms. We need to know that too. And we need to know how big the population of people susceptible to the virus might be.
So far, that appears to be everyone with hands, a mouth, and a nose.
So I've just shown you that in the last 2 decades, we've seen worldwide that the average detection of outbreaks has been speeding up very quickly. We have some innovations that I'll be talking to you about that are part of the reason for this, but they are not the entire reason for this. One of the biggest reasons is that health systems around the world have gotten better and routine reporting has gotten better. But I want to talk to you a little bit about what we did at Google and why we did it and what that's led to. These are informal sources of disease reporting. The most important thing to say is that until the change in the international sanitary regulations in 2006, David, is that right? WHO was not allowed to take cognizance of an epidemic anywhere in the world unless it came from the health minister of a country. Now, WHO is required to take action when any one of these informal systems report a new epidemic. It's a tremendous sea change. That one political change has opened up the floodgates. And now we can see internet searches, health scrubbers, self-reporting, social networks. In fact, these are all organizations which did not exist 10 years ago. And they are there trying to look at all the news media, capture keystrokes, exchange SMSs, use your cell phone to help identify new potential pandemic diseases. And Health Map, which is one of the organizations, displays that information on an hourly basis. You can take a look at the map. It's free. It's online. And you can see any disease that you're interested in. The work that we did at Google was based on 3 young engineers who knew of my interest in speeding up disease detection. And they came to me and they said, why don't we look at every single search term that's ever been entered into Google in its entire history and do 300,000 or 400,000 simultaneous multiple regressions and figure out exactly what 50 terms will explain the entire variability in influenza reporting. And I said, sure. You'd say sure. And in fact, they did. And we took CDC, the Center for Disease Control's 5-year truth data, trained the system on that data, and they, in fact, put together an algorithm that beat CDC's reporting by 2 weeks. And Phil Campbell, who's the editor of Nature magazine, when we sent that to him, he put together a great peer review panel for that, and he said, they reported back, they said, this is a really good experiment. Would you please find another lab that has 10 million computers and has 50,000 trillion bits of data in which we can verify your report? Fortunately, he was willing to accept that that might not be possible. But we ran that for 1 year before we announced it to the public, because we were afraid if we were wrong and we gave bad information, it would alter people's behavior about taking the vaccine. So here's how it works. You can see ILI means influenza-like illness. That's CDC's reports in yellow. That's what Google Flu Trends shows in blue. Those are actually all happening at the same time. That's one point in time when Google seems to suggest that there's more flu than CDC does. And now watch how CDC's reports are changed the week later as additional laboratory confirmation comes in. What's really interesting is that we use Google to be a surrogate for truth data that came from the health agency, and then a drugstore firm called Walgreens used its prescription data, and it used as truth data Google's data. It's a whole new world with all these new systems. That's why I started by saying modernity might have been the cause of increased pandemic risk. Modernity can be the solution for increased risk. Next week, we are announcing a new surveillance system. It's called Flu Near You in the United States. We're announcing it at the American Public Health Association. It will be based on getting a SMS text message once a week. Volunteers will be asked if they'll receive it, and they're willing to say if they're sick or not. That's it. Based on that, we think we can beat CDC's reports of influenza by 2 weeks. And with each successive increase in technology innovation, I hope we can continue to do that. But it's not just CDC, it's not just Google, it's not just Flu Near You. The world is erupting in new and innovative ways to find every new pathogen as and when it emerges. And so that's where we are right now. And to summarize, if we do nothing, we are likely headed to a world that is an age of pandemics. And pandemics are really terrible. When we talk about a pandemic, we're not just talking about tens of millions of people dying. We're talking about no airplanes in the sky for 6 months, no supply chain. There'll be nobody going to work at Google's call centers or Yahoo's. There'll be no internet. The apocalyptic vision that I gave you in the beginning will come true. But it doesn't have to happen that way, because we have new tools that we can apply to fight against that occurrence. And digital disease surveillance is one. New self-reporting systems are another. Better vaccines, point-of-care diagnostics, better government organizations, increased general public health services. And as you think about this, and you think about these two paths that stand before us, just ask yourself, which of them is the highest and the best path that we can follow? And remember that in dealing with pandemics, as in dealing with so many other things, we are really all in this together. Thank you very much.
Larry, that was brilliant, as I anticipated, and both a source of enlightenment but also inspiration as the potential to deal with these problems. I'm delighted we're joined by a panel now. David Heyman, who is the chair of the board for the Health Protection Agency in the UK, who is a professor of infectious diseases and epidemiology at the London School of Hygiene and Tropical Medicine, and also the head of the Global Health Program at Chatham House, previously the Assistant Director General for the Health, Security and Environment Operations at the WHO, and as you heard, was an old colleague of Larry's in India. He'll speak first on the panel. He'll be followed by Professor Adrian Hill, who's the director of the Jenner Institute. You saw mention of Jenner in Larry's slides. And I'm delighted that Adrian is also the co-director of the Oxford Martin School Institute for Vaccine Design. And then thirdly, we have Professor Rodney Phillips, who's a distinguished professor of medicine in Oxford and is the co-director of the Oxford Martin Institute for Emerging Infections. Please do join us. So I'm going to ask first David for some comments, and we'll go around the panel, and then we'll have a little discussion and open it up to the floor.
Thanks very much. Larry clearly focused us on the animal-human interface. These diseases many times come from an animal into human populations, and then they set up residency, and they continue to transmit. I'd like to take you to 3 examples in the 20th and 21st centuries of this type of disease, understanding that probably every disease, or most every disease that's in humans today, came at one time across that barrier from animals into humans, be it tuberculosis, be it smallpox, or be it HIV. And I'd like to take you first to HIV in the early 20th century, when somehow it came from a non-human primate into a human, possibly when an animal was butchered for food, possibly when it was hunted. And it was able to set up residence in those humans, mutate slowly, change itself into a form which could then transmit indefinitely. There were several things that favored this. Number one, it had a very long incubation period before people got sick, but it was a very severe disease. Then fast forward to 1976, another disease first identified, Ebola hemorrhagic fever. This disease has never taken up residence in humans because it has a very short incubation period from the time of infection to onset of disease is a matter of days, and it's a very lethal disease. Up to 90% of people infected die. So it's been its own worst enemy, and it's not been able to set up residence in humans and transmit from human to human. The third one I'd like to talk about is SARS. And SARS was a disease which emerged in the early 21st century. And this was a disease which was caused by a virus which mutated one time, either in a human as it was reproducing or in an animal as it was reproducing. It crossed the barrier from animals, probably civet cats, maybe bats earlier, into humans, and then it was able to transmit and spread throughout the world. It was stopped. It did not become endemic. But SARS is a very good example of a disease which was a disease that was present in human populations in a less virulent form. 22% of market workers in China were shown to have an infection that was a coronavirus, probably the precursor of this SARS virus. So these are three different examples. Viruses, some became endemic or set up residence in humans, others don't because they're too virulent, and the third one was stopped. Now, this SARS example is a good example of what we know about a disease. We know that this disease was occurring, it was transmitting regularly in a less virulent form. Today, when one of these outbreaks occurs, as Larry said, it's important to detect early and respond rapidly. But think of what could have happened in China had they been paying attention to what was going on at the human-animal interface. They could have set up a set of regulations which made market workers more attentive to what they were dealing with so they wouldn't get infected if it had been known. There could have been a whole series of things. And so in addition to detecting diseases earlier, there's a possibility that we could shift the paradigm from rapid detection in humans and rapid response way back to stopping these diseases from occurring in animals by using the determinants of these diseases to understand. We know that these diseases can transmit to humans. How do we best deal with the animals to prevent that emergence into humans? So rapid detection, rapid response is very important. Understanding what's going on in animals is extremely important, but it's also important to understand why these emergent events occur and try to get back and prevent them through better practices in animal husbandry, in human medicine, in trade, in all types of things, including food preparation. But the most important emergence which is occurring now is one that's very silent, and that's antibiotic resistance. You know about it here in the UK very well. It's an emergent infection. It's become endemic throughout the UK, throughout the world. C. diff, many other organisms have become resistant. So though we try to detect and respond early, these diseases know how to cross that barrier, to get into humans or to in some way interfere with our medications and vaccines we have and establish themselves and continue to transmit.
Thanks very much, David. Adrian.
Thanks very much. So you heard about very substantial progress in the face of a pandemic in the time that it now takes to identify the relevant causative organism. When HIV came along, it took us years to identify the virus in the 1980s. When SARS came along 10 years ago, it was much, much faster. You've seen the data. It's down from six months to 3 weeks. And we can probably do even better than that with new nucleic acid amplification technology. So that's the good news from my perspective. We'll know what the target is. It's the really bad news that I want to highlight. We've seen a pandemic in the last year. It was of flu, and a vaccine was developed. But it took 6 months, 9 months. Not that much vaccine was generated. And that's probably, I would argue, the best case scenario. We know how to make flu vaccines. We make them all the time. Industry is set up to sell flu vaccines. They know how to do it. And they know how to change the vaccine every year according to the strain that is prevalent. And there's no other vaccine that we use in that way, where we tailor it every year to what's circulating. So if it takes us 6 months to make a new strain of flu vaccine, when there's huge global panic about a new swine flu pandemic, what would happen if it were a virus we didn't know about? And again, we have a bit of evidence from the SARS outbreak. There was work on vaccine development for SARS. It wasn't close to being useful. A rapidly transmitted virus, we had to contain it in traditional ways. So the worry is, if it's a new virus and we're getting new viruses emerging from other animals at the rate of several a year now, how long would it really take us to design a new vaccine, to manufacture it at scale and distribute it worldwide? So the short answer is we don't know. The real answer is a very long time, because why? Well, we know how to make vaccines, don't we? We've been doing it for generations. Well, if we did, we'd have vaccines against HIV, against malaria, against hepatitis C, very common pathogens that we know an immense amount about. We don't know how to make a vaccine against us. So we may not be able to do it quickly or at all. More likely, we will be able to do it, but we won't immediately know how to do that, and it will take lots of different attempts, usually sequentially in the real world of research and development. What would happen if there's a real panic and WHO was trying to coordinate a vaccine development program? Well, it would be a bit like it was last time. There'd be a bit of quiet negotiation with one company and another company. They'd want to know how much money they were getting, what was the real market. Maybe it would peter out. Should they invest hundreds of millions of dollars in something that might be gone or controlled, like SARS was? So who's going to underwrite them? WHO doesn't have the money. And even if they decided to take this on, what you really need is parallel attempts from many different groups around the world working with different systems and different technologies to make a vaccine. And there's absolutely nobody out there charged with controlling that or coordinating that. And then say you get to something that looks kind of promising and you want to manufacture it. Where are you going to manufacture it? We do make hundreds of millions of doses of flu vaccine every year. We don't make hundreds of millions of doses of anything else, really. There are nearly 7 billion of us. It might take 2 or 3 doses to vaccinate against whatever comes along. We have nowhere near to the manufacturing capacity that we would require, even if we had something that worked. So, to sum up, we've got a problem. There's no central coordination of response in terms of vaccine design, development, and manufacture. We're up against regulations that do everything they can to maximize vaccine safety so that no healthy individual is harmed. And what that means is delay. We have safety standards appropriate for vaccinating you to make sure you don't get flu. You want an absolutely safe vaccine. In a pandemic, when there's a global emergency, somebody's got to decide on the risk-benefit analysis as to whether you do all those tests, and who decides, and what risk is appropriate to take, and how long would it take people to agree. None of that is clear. The best way of thinking of it is if you were going to stage a bank robbery and you're going to hold the bank up, you'd have a car outside with the engine running, ready to get away. We're in a situation where we don't even have the driver, we don't have the vehicle, we haven't built the car, we haven't built the manufacturing facility. We don't know what we're going to do in that scenario. And several people have spotted the problem, but nobody's really got the answer.
Thanks very much, Adrian. Adrian, by the way, I've always thought of as being a vaccine optimist. So thank you. And of course, running remarkable work in Oxford on vaccines, doing many great things. Rodney.
I think I really would like to talk about one simple aspect of the type of biology we're talking about. And one of the reasons that we have to remain profoundly concerned about the risk of these sorts of pathogens. Many of us in this room are genetically different, but the stability of our genes is because those genes are made of a relatively stable nucleic acid called DNA. And although variation in DNA is so obvious as we look around, it's a remarkably stable material compared with the other form of nucleic acid, RNA. some of the things we're talking about are not composed of DNA. They aren't stable in the way that that substance is. The viruses, for example, HIV and flu virus, are encoded and encode their proteins with RNA. Now, this might sound like a chemistry lesson, Vice Chancellor, but this creates an enormously important distinction in terms of the risks of these organisms. Viruses which encode their genome in RNA have the capacity, while copying themselves, to create an enormous error rate. Many of those errors lead to the virus being non-functional and are an endpoint, but some of the errors simply create new mutants. And so when an RNA virus passes through its animal hosts and through human hosts, it has an enormous capacity to generate variation in a blind fashion, but that variation at times can provide it with advantages rapidly. And so in the case of HIV, a single drug therapy for that infection leads to a very rapid emergence of drug resistance. 2 drugs applied to that virus leads to very rapid emergence of drug resistance. It was only by locking the virus with 3 drugs, an achievement in 1996, that led to the very effective treatment for that virus. But if the drugs are misused, then as with antibiotic usage, the benefits fail us. So I think for this discussion, I'd just simply like to make that rather critical biological point that pathogens which encode their genomes with RNA provide an enormous difficulty, both in finding stable vaccination, providing stable drug treatment, and indeed allowing the host to catch up with their genetic change. So in the case of hepatitis C virus and in the case of HIV, these viruses can outrun the human immune system, and so they provide us with an enormous challenge. Finally, Professor Hill, with his extreme application to vaccination, I think would have to agree with me that if you wanted to vaccinate against something successfully, an RNA virus wouldn't be your first choice. Thank you very much.
Thanks very much, Rodney. We really are privileged to have this panel here today, and Rodney was amongst the first to discover how HIV-1 evades human immune systems. So the people that are on the panel really are at the cutting edge of this science. Larry, do you want to come back on any of this?
I do. I think that it's thrilling to have a conversation like this, and especially here at a great research university. And if we look at what will it take to motivate the world to make the kind of plug and play, immediately available, always there vaccine that Rodney knows that we need, and we all know that we need, and what will it take us to fully articulate the differences between RNA and DNA pathogens and understand how they work in different ways? And as David talked about, what will it take us to push the frontiers of medicine and public health into One Health, this field of emerging consciousness where animals and humans and the environment all share the same risks and costs and benefits? There's always a motive engine in history, something that makes us want to do more research, that makes governments fund research, that makes foundations open up their coffers to do research. When you had an automobile, research on asphalt increased because roads became more valuable. When we had an agreement that we were going to work together as a world to eradicate smallpox, innovations in the kind of needle, the freeze-dried vaccine, all the infrastructure that was necessary to eradicate smallpox came into being. I think that if we are able to truly push the time that it takes to find every new potential pandemic pathogen down to single-digit days, we will be finding more pathogens. We will be inspiring optimism that all of the other aspects of this public health enterprise is worth investing in spades. And that makes me very optimistic. Because unless there is that motive engine occurring in the field in history, seeing the results, then research is done by true believers. All of us are true believers. But it isn't done by society as a whole. I think we have a chance now. I think we are very close at the cusp of seeing a revolutionary breakthrough in the way public health and in the way pandemic prevention is funded. And this is an extraordinarily thrilling conversation.